Hey guys, Mr. Betts here. I want to talk to you about something in this video called Euler's method. So before we get started with the actual calculus, Euler's method is named after a guy named Euler, Leonhard Euler, and Euler is often mispronounced. So it's pronounced like that word, Euler, but spelled Euler. And Euler's method is something that we can use to kind of extend the idea of linearization. So before we get into Euler's method, let's just refresh how linearization works. So first of all, linearization is good at approximating the value of a function near a point of tangency. So in the picture right here, we have a point of tangency, and we can use the tangent line to approximate the value of the function. And you can see that the point on the tangent line and the point on the curve are pretty close to each other. So as long as we're close to that point of tangency, finding a point on a straight line is going to be a pretty good approximation. And the way linearization worked is basically saying that the slope of a secant line is going to be approximately the same as the slope of a tangent line as long as we stay pretty close to that point of tangency. So this delta y over delta x is going to be a change in y over a change in x on the function. And that slope through the secant line is going to be pretty close to the slope of the tangent line. So the idea of linearization here takes this formula right here and says that a change in y could also be written as, say, f of x minus f of a is going to be approximately equal to the derivative at some point times x minus a. So this equation right here is equivalent to that expression right there. And so basically it's saying the slope of the tangent line is pretty close to the slope of the secant line. The problem with linearization is, even though it's usually pretty good around the point of tangency, it is not very good when we get further away from the point of tangency. So what we want to do is come up with a way to take into account that the slope is changing as the x values change. So even though the slope here might be roughly maybe 1/2, the slope is increasing and increasing, and the slopes are getting bigger and bigger as we move to the right. And so Euler's method is going to be an approximation method that takes that into account. So if we take a look at a slope field here, the differential equation for the solution to this curve is showing us that the slopes are increasing as we move to the right. And so what Euler's method is going to do is say that the tangent line is going to be a pretty good approximation for a little bit, but as we get further away, we want to take into account that the slope has changed. And so the slope after we've moved a little bit has increased, so we're going to increase the slope of our approximation. And as we move a little bit further away, we're going to say, okay, well, let's reevaluate and look at the slope as we move further away. So when linearization just uses the slope at the tangent line for any period of x, any interval, the process of Euler's method is going to take into account that the slope could be changing. And you can see here that straight line approximations for shorter subintervals are giving us a much closer approximation. So the error that we get here is a lot less than if we just use a straight line approximation. So the idea of Euler's method here is going to be essentially the same as linearization, except we're going to take it in steps. So with Euler's method, we're going to be given a differential equation, we're going to be given an initial condition, and we want to approximate the value of the function at some other point, but we're going to use a certain number of steps. So we're going to determine the size of each step. Then we're going to essentially apply that same linearization formula, but we're going to apply it for one step at a time. And we're going to repeat that until we get to the point f of b. So I'm going to go through this process with a few examples in future videos. So I would encourage you to take a look at those videos to get a better idea of how we would apply that with specific examples.